In the previous video, we isolated processes using namespaces, but here's a problem. Even an isolated process is still using the same file system. So if you run an application right now, it can still seize your entire system. That's not a container. But the real question is, how does container get its own slash drive? Because when you run something in Docker, it feels like a completely separate machine. So today we are going to build that file system from scratch. So no Docker, no images, just a pure Linux. Before we try to change anything, we need to understand what slash actually means. So if I run ls/, so it will list down the multiple directories which is under the slash drive. So this is not just a directory. This is the starting point of the entire file system. So every path in Linux like /etc/passwd, /usr/bin, all of them are resolved from the slash only. So when a program accesses a file, it does not think in terms of host or container. It simply follows a path starting from the slash drive. So if slash changes, everything changes as well. So let's prove that. If I run cat etc/os-release. So this program is not doing anything special. It's just reading the file from /etc. So if this /etc was different, the output would also be different. That means program don't know where they are. They only know what slash shows them. Now let's connect this to a processes. So for that, if I run ps aux and head. So each process here is running a binary like /usr/lib. These paths are resolved from slash drive only. So now we can combine two ideas. Processes depend on the file system and file system depends on the slash drive. So it means if we change in the slash, it changes the process environment all along. So let's see the current state. So if I run ls/root. So right now this process can see everything: user file, configurations and system data. And there is no boundary here. Every process shares the same root file system. So if you run an untrusted application, it can see everything. So now we fix this. Instead of sharing slash, we give the process its own file system. But here's the catch. We are not going to create a new kernel or we are not going to create a new VM. We are just creating a different directory structure. So first of all, let me clear out the screen and create one directory, that is mkdir, and so I'm going to create a folder that is rootfs-demo, and the directory got created. Let's go inside this, and I'm going to create a couple of directories here. So I'm using a mkdir command, mkdir-p bin lib64 etc proc and the usr. So what we just created is not random folders. This is the structure of a Linux system, and this is exactly what a container image contains. Now let's make it usable. For that, let's copy the binary files. So first of all, we are going to copy the bash binaries. So for that, we are going to copy the bash binaries. So we can use cp command and the path of that, which starts from /bin/bash, and I'm going to copy it into the bin folder. So if I do ls here, we can see all the 5 directories got created, and under the bin, we have a binary of a bash. As we can see, it got copied. At this point, we have a file system, but no working system yet. Try to imagine running bash here. It will fail. Why? Because binaries are not standalone. They depend on the shared libraries. And to identify the dependencies of the shared libraries, we can use LDD and the bin bash. So each line shows a required library and where it is located. The binary is just an entry point, and the real functionality comes from these libraries only. Now let's copy it one by one. For that, I can use cp-av and the path of these libraries. So let's copy it here, and I'm going to copy it into the lib64 directory. So here, if you notice, I have used -a option. So it means it preserves the symbolic links as well. And this matters because many libraries are not real files. They are links to the versioned files. So that way we need to preserve the symbolic links so that it can work properly. Because if we break the link, the system will break also. So now let's copy the complete set of files. So cp-av. So it will copy all the files which is placed under that particular directory. So that's why I use a wildcard here. I'm just going to overwrite it. So as we can see, it copied the 2 files. Similarly, I will copy another libc library as well. So it also got copied. And at last, I'm going to copy the last library. That is this one. So if I run ls lib64, we can see the 4 library got copied here, and along with that it is having a symbolic link. If I run ls-l lib64, and we can see it preserves the symbolic link as well. That's why we have used the -a option, so it will not break the links and the system as well. Now let's copy the another command, that is ls. For that we can use cp/bin/ls and to our bin folder. Now instead of manually copying everything, we can automate it. For that I am using a command. So this command finds all the libraries required by ls and bash, filters the valid paths and copies them into the root file system. So here if you see, I used ldd, that means list dependencies of bash and the ls binary, and then I am using the awk command to extract the file paths, and I'm removing the slash from there, and cp copies everything in one go. So if I hit enter here, so as we can see, it automatically collects and copies all the required binaries. So this command just automates dependency copying. Instead of guessing libraries manually, we extract and copy them in one go instead of doing it manually, which we just did for the bash binary. So now our root file system is ready. So let's go one directory back. So this is our root file system directory. So we try to use this as a file system. So for that we can use chroot, the directory path, that is rootfs-demo, and the /bin/bash, and I'm exporting the path along with this, that is equal to /bin and exec bin/bash. So let me explain this command very quickly, because from this point on, this process will treat rootfs as a slash only. So here if you see, I have used chroot, that means change root to our file system, and after that I am specifying the /bin/bash, that means runs the shell inside it, and after that I am specifying the export path bin, that means it ensures commands like ls will work, and at last I am using exec/bin/bash, that means it replaces process with a clean shell, and without setting these paths, command will not work because shell won't know where to find binaries. So that means this command switches the root file system to our custom rootfs file system and starts a shell inside it and makes the process believe this is the entire file system. So let's press enter here. So now we are inside our custom root file system, and if I run ls/ here, so notice something interesting here. Bash is working but ls is failing. So this tells something important. The file system exists but it's incomplete. So we copied the dependencies for bash but not all dependencies for ls. Even though we ran the ldd command to find the dependencies of bash and ls, but some libraries are missing like libcap. So each binary has its own dependencies, and if even one is missing, it won't run. So let's exit from the chroot. So let's find the dependencies for the ls binary. For that we can use list dependency command and give the path of /bin/ls and grep for libcap. So here if you see, we got the path. Let's copy it very quickly. So cp-av and to the path, that is rootfs and the lib64. Let's do the overwrite here, and let's copy all the files which is under there with the libcap name, so it will not throw an error again if some another file is missing or required over there. So let's see, it's overwriting it. So if you see, it copied the another file, that is 2.69. So let's run the chroot command again. So chroot. So again we are inside the custom root file system, and if I run ls/, so it again failed but with a different library, because ls is having a multiple dependencies internally. So this confirms something important. Every binary depends on multiple binaries, and if we haven't copied all of them yet, we will face an errors. Even though we try to copy dependency, but some libraries are versioned, simplinked and located in different paths. So manual or partial copy missing these things. So let's copy the pending dependencies as well. So let me come out of it, and I'm going to run the same command again, and that is this one. So we copy it to the lib64 again, because that's where these libraries are expected. And along with that, I'm going to copy lib dependency separately, which we have found from this particular command. So let me paste the commands here. So it's already there. Let's override it. So now all the dependencies got copied to the lib64 directory. Let's run the chroot command again, and let's see how it works. So now again we in the custom root file system, and if I run ls/, now it worked not because of the chroot, but because of the file system is complete and it has all the dependencies of ls and the bash. Bash was already working because we have copied all the dependencies, but ls was having some issues. So we fixed it by manually copying those files to the lib64 directory of our custom root file system. And this is exactly what container images solve. They package everything together so you never see missing dependencies error. And this might be an issue while minimal images sometimes break because they miss dependencies of some core commands. And if I run ls/home, we won't be able to access it because we haven't created any directory called home inside our custom root file system, because we are not getting anything from the host system, because /home is always available on the root file system, but on our custom environment we don't have anything with the home directory, because home refers to the rootfs-demo/home, not the host directory, that is /host. So this looks like a container, but it's not. We only change the file system view, but processes are still shared and kernel is also shared. We changed what process can see, not how the system is isolated. Now let's connect this to a real container. So let me come out of it. So now the question becomes, can we isolate processes the same way we isolated file system? So now let's try it in our container. So first of all, let me clear out the screen. So now I'm going to create a new container using the unshare command. So unshare -pid -uts -mount -net -fork and -mount -proc and /bash, and let's press enter. So we are inside the container. So if I run echo $, we can see the process ID 1. And if I run ls here, so we can see all the files from the host system only. But now we need to add our own custom file system. So for that we can use the chroot command which we just ran earlier. So here I'm using exec chroot rootfs-demo and the /bin/bash. So let me explain it very quickly. So here I'm using the exec that replaces the current process instead of creating a new one. So there will be a no child process and the PID will remain same. And here I am using the chroot and the custom root file system. So that changes the root directory to our custom file system. And at last I am specifying the bin bash that starts a shell inside that environment. So we are replacing the current process with a shell that runs inside our new file system. And let's press enter here and echo $. So as we can see, we are still PID1, which means we didn't create a new process. And if I run ls here again, so as we can see, ls command is not working because we didn't set the path. Earlier in the chroot command, we specified or exported the path using the /bin, but in this command, we didn't perform that operation. So let's add the path very quickly. So export path equal to /bin, and if I run ls here, so this time it worked because the shell needs path to locate commands which we didn't specify in our chroot command. That's why we need to explicitly exported the path for that /bin. So the container don't just need files, they also need a proper environment. And that's why container images define environment variables. So Docker automatically set path inside the container using the Docker file only. So that means our root file system has a path, but system doesn't know where to locate. And that is the issue we face this command not found error. So now we have isolated the process and the file system. So now if we create a network stack here, like creating a VF pair and assigning an IP address on this particular container, so we can do that, and we can also specify the host name using the UTS namespace because we have specified the same in the unshare command. And that particular demo I have already did in very much detail in my previous video, so that you can get a better clarity to set up a network along with the host name of the container. Right now it will not work because I haven't copied the host and the another binaries which will be used to set up the network configuration. So we did everything manually. We built file system, we isolated processes, and we created an environment as well. Now let's connect this to a real system. So let me come out of it. So we are inside our host system. So when we run docker run nginx, so Docker does a lot of step at the back end. It prepares a root file system from image, it creates namespaces, it sets up networking, and it starts the process. Exactly what we just did, but in an automated way. Everything we just did is a manual way, but Docker automates the same process. And similar thing happens with the Kubernetes. Kubernetes doesn't run containers directly. It uses container runtimes like containerd, runc, or the Docker. And these runtimes perform the same step like namespace setup, file system setup, and the process start. So Kubernetes orchestrates and Linux does the actual work. So now let me show you where this file system actually come from in the containers. So let me pull the images first. So podman pull nginx. So this downloads the container image, but what exactly is an image? It's not magic, it's just a package file system only. So let me save it. Podman save nginx -o and nginx-image.tar. So now we are exporting that image into a tar file, basically turning it into something we can inspect. And now let me extract the image. So for that, let me create one directory, that is nginx-img, and let's run the tar-xf and nginx-image.tar to a directory which we just created, that is nginx-img. So the image got extracted under this particular directory. So let's go inside this and let's open this. So we can see a different tar file along with some directories. So here we need to find the layer.tar. So find.name layer.tar. So this finds the image layers, and each layer represents a set of file system changes. So let me press enter. So here if you see, these are the image layers, and each layer represents a set of file system changes. So instead of storing full file system every time, container stores only what changed. So let me extract this very quick using the tar command. So tar-xf the path. So it got extracted, and let's press ls here. So look at this very carefully. This is the full Linux file system /etc/home/lib/lib64, and this should look familiar because this is exactly what we built manually. The only difference is this one is automated. So now everything connects. When you run a container, the system take this file system, set up a namespaces, and start a process inside it. So that means file system, process isolation, and execution, that's a container. At this point, we build a file system a container uses. But here's a catch. Do we really copy this file system to every container? That would be a slow and a waste of space. So how do containers resolve this? So RootFS gives a container a file system, but OverlayFS makes it scalable. So in the next video, we are going to understand how we can make it efficient using OverlayFS. If you found this helpful, hit like, share it with your friends, and subscribe for more content like this. Thanks for watching. I will see you in the next one.